Physics 20s. We're going to talk about gravitational fields today. Hopefully you can hear me, and if at any time you need to stop the video to catch up, feel free to do so. We'll start here quickly with coloring the outcomes. So we're going to talk about gravitational field strength. In order to do so, we have to define two things, and that's action at a distance forces. So we need to know what is meant by an action at a distance force. I've talked about that before. Define field. Determine gravitational field strength from a formula we are already familiar with, so that's a calculation outcome. Define the direction of the gravitational field as the direction of the gravitational force experienced by a test mass. Draw gravitational field lines around a single mass. State that the gravitational field strength is equivalent to acceleration due to gravity at a particular location. Relate metric system units to physics quantities, so that's acceleration due to gravity in meters per second squared or Newton kilograms. We're going to do a unit analysis to prove they're the same. Calculate gravitational field strength using a new formula, G equals big G times m over r squared. Derive, oops, that's a standard of excellent outcome. Hopefully that didn't, I accidentally hit stop instead of highlighter, so hopefully that didn't interrupt it too much. And solve for any variable in the field formula where you have to add distances together to get r. So the first thing that we're going to talk about is the fact that gravitational force is an action at a distance force. So what that means is it's a force that acts on an object without contact. So it acts on objects. Really, like what happens is it acts on objects with a couple of mediating particles, which we talked about yesterday. So it's also called a non-contact. So physicists had issues with trying to figure out how it was that an action at a distance force could work, like how a force could have an effect on an object without any contact. So a guy named Michael Faraday came up with the idea of a field. So this is Michael Faraday. You'll talk more about him in physics 30, about electromagnetic induction. He's really important with electricity. So he came up with this idea of a field. And field is a model. It's a model is something that describes a phenomenon in a way that makes it easier to understand, but it has to like hit all points of the phenomenon. And it isn't something that actually exists. So a field doesn't really exist in space the way a force does. It just describes how it is that a force can exist at a distance from an object. So a field is a model that describes a three-dimensional region of influence due to an action at a distance force. So it tries to explain how a force can act far away from the object. Let's just say how a force can act far away. A field is represented by vectors, so field lines pointing in the direction of the field. So those are like, we're talking about arrows here. The field is stronger where the vectors are closer together, and a field can be attractive or repulsive. So you're going to talk about three fields in your physics career: gravitational, electric, and magnetic. Gravitational is only attractive. Electric is attractive and repulsive. Attractive and repulsive, as is magnetic force. It is attractive and repulsive. And a test object is something that we use to define the magnitude and direction of the field. Okay, so it's just something that experiences the field without actually having its own field. Okay, so it experiences a force without having its own field. So forces and fields are different. A force actually exists. It's something that actually acts on an object. A field is just the opportunity for a force to exist. Okay, sorry, that's covered up there. We'll try to move this around here. So a gravitational field is a region of influence then that surrounds any mass. Any object has mass, so all objects, because they all have mass, will have a gravitational field. We tend to think of it in terms of the Earth, though. So if I draw the Earth, actually I'm going to cut this so I have a little bit more space. So really what we draw is we draw the object would be circular. So let's say this is the Earth. And then the gravitational field lines are going to be drawn the way a test mass would go. So first of all, gravitational field is attractive only. So the field lines always point towards the object creating the field. It has an infinite range, meaning there's no limit to it, although it gets weak at a big distance from the object. A test mass will accelerate towards the object at a rate equal to the acceleration due to gravity. So G on Earth, G equals 9.81 meters per second squared. But say if we're talking about the moon, G is 1.6. Okay, so field lines always point towards the object. But let's say we have a little test mass, a little guy in different spots around. You don't have to draw on the test mass. This is just to illustrate it. So let's say our test mass is a little astronaut at various spots. The direction of the field is the direction that astronaut will go if he's just allowed to be. Right? And he'll accelerate towards the Earth at a rate that approaches 9.81 meters per second squared. It gets to 9.81 meters per second squared once he's on the surface of the Earth. So we've already used a formula that includes gravitational field strength. We've used it with meters per second squared, but G is also known as gravitational field strength, which is measured in Newton kilograms. And so we have what's called the test object formula. So that means that you know information about the object in the field. So this would be information about like our astronaut that is somewhere, some distance away from the Earth. So the test object formula, it's the one that we're familiar with, that we've been using already. It's on your formula sheet as G is equal to Fg over M. So G is your gravitational field strength in Newton kilograms. It can also be written in meters per second squared. Typically we use meters per second squared when the object's accelerating, like when we did vertical dynamics. When we're just talking about field strength, Newton kilograms is a little bit clearer, but the units are the same. One is just in fundamental units and one isn't. Fg is gravitational force or the weight. Should have that extra on it. And M is the mass of the test body experiencing the force. Okay. Acceleration due to gravity is measured in meters per second squared. So this is like i.e. with a free body diagram, like an elevator going up or down. Gravitational field strength is measured in Newton kilograms. Okay. And we're just going to do a unit analysis to prove that the units are the same. So what we want to do here is we want to start with Newton kilograms, and we're going to work our way to meters per second squared. Okay, just by replacing variables in Newton kilograms with, units in Newton kilograms with units that they can be written as. So what I mean by that is we have a formula here that says F net equals M times A. So that's a Newton equals a kilogram times a meter per second squared. So I'm going to write, instead of writing Newton, so I'm just going to fix this so it's this way. So it equals Newton over kilogram. I'm going to write a Newton as a kilogram times a meter per second squared. Then that's divided by a kilogram. Well, then the kilograms cancel and just start with meters per second squared. The units are equivalent. Again, if I'm going too fast, because I am trying to get this done before school Tuesday morning, just stop and start it as much as you need. So we'll do an example here with that formula. So an 80-kilogram astronaut weighs 303 newtons on planet X. What is the gravitational field strength on the surface of planet X? So we know the mass of the astronaut is 80 kilograms. The weight of the astronaut, or the force due to gravity that he experiences, is 303 newtons. And we want gravitational field strength. So pretty simple calculation. Big G, whoops, sorry, getting ahead of myself. G equals FG over M. So 303 newtons over 80 kilograms, which is 3.8 Newton kilograms. It would not be wrong if you wrote meters per second squared. I wouldn't take marks off for that. What we want to do now is we want to derive a formula that we can use. So let's say, like, we have our situation where we have our object, or our object creating the field. So let's say this is Earth, and then we have our test object far away. Because that leg got moved over. Okay. Let's see if I can do this with his legs like that. Nope. So we just make him crooked. Okay, yeah. So no way to get him so that his legs aren't in the right spot, because it didn't orient my board. So the first formula we use, the FG over M, that's if what we know is stuff about the guy, the object outside in the field. If we don't know anything about the object outside the field, so if we only know info, so if our info is about the object making the field, we might be able to come up with a formula to use that. So we have two formulas we've used already. We have FG equals M times G, and we have FG equals big G times M1 times M2 over R squared. When we're talking about test mass, or the object in the field that's experiencing a force, that's this force here, which I'm going to call mass 2. Okay. So mass 1 in the force in this formula here, the force of gravity formula, G M1 M2 over R squared. Mass 1 will be the object creating the field. So this is mass 1, this is mass 2. Okay. But the force, whether we use the first formula or the second formula to calculate the force, we get the same number. So if these FGs are equal, then we can just make cross out the FGs, and we can make M2G equal to big G times M1 M2 over R squared. So then what happens is we end up with the test object mass on both sides of the equation. So actually then what happens is we don't need it. So we can cross out the two test mass from either side of the equation, and we're left with G equals big G times M1 over R squared, which is the source mass formula. And it's for when you have info about the object causing the field. So G is your gravitational field strength in Newton kilograms. Okay. M is the mass of the source planet. R is the distance from the center of the planet, and then big G, of course, is your gravitational constant. So you don't need any information. You don't even need a test mass for there to be a field. So even if you don't have a test mass, all you have is your source mass, so this is M1, and you have some position in space where you want to find what G is. Doesn't matter if there's an object where G is or not, as long as you know mass 1, and as long as you know the distance from the center of mass 1 to where you're trying to find the field. So we'll just do some examples using this formula. We want to calculate the gravitational field strength on the surface of Jupiter. Okay, At this point, I realize now you need a handout. So I'm gonna pause the video here, or I'm gonna have you guys pause the video. Somebody pause the video, and your sub is going to hand out a chart that has all the information about planets and then some common planets and their moons. So on the front side of the page, if we look at Jupiter, we need to know the mass of Jupiter on this sheet is 1.90 times 10 to the 27 kilograms. And the radius, we want the equatorial radius. Orbital radius is how far it is away from the sun, and so the distance between the center of Jupiter and the center of the sun, and what the radius of that orbit is. Equatorial radius is the distance from the center of Jupiter to the surface of Jupiter. So the radius of Jupiter is 7.15 times 10 to the 7 meters. And we want gravitational field strength. So G equals big G times M1 over R squared. So 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of Jupiter, which is 1.90 times 10 to the 27 kilograms divided by 7.15 times 10 to the 7 meters squared. And you get 24.8 Newton kilograms. So if you're just standing on the surface of Jupiter, that's the acceleration due to gravity, or the gravitational field strength you feel. So you'd feel about almost 3 times heavier as you would on Earth, about 2.5 times heavier as the gravity is stronger. So we can also, this is the one that would be considered a standard essence question, because you're having to figure out the gravitational field strength at a distance away from the surface. We did a question like this with force. So what we have is the Earth, and we know the radius of the Earth. And now what we're told is that we want to figure out what G is at a distance of 600 kilometers from the surface of the Earth. So that means our R here is going to be the radius of the Earth, 6.37 times 10 to the 6 meters, plus 600 kilometers, which is 600,000 meters. So we get 6.97 times 10 to the 6 meters. And again, our mass is the mass of the Earth, 5.97 times 10 to the 24 kilograms. So G equals big G times M over R squared. 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Move this over. Times 5.97 times 10 to the 24 kilograms divided by 6.97 times 10 to the 6 meters squared. I also at this point I should point out that on that handout, the planets handout, the mass of the Earth is written as 5.9. It is 5.97. It's the radius, equatorial radius of the Earth. I've crossed it out and written the one that's on your formula sheet, just so you don't confuse. Okay, and if we're a big distance away from the surface of the Earth, then we would expect the gravitational field strength to be less than it is on the surface of the Earth, as it is at 8.20 Newton kilograms. At this point, you can stop the video and take maybe about 10 minutes to try the first 5 questions in your workbook. So page 255 to 257, numbers 1 to 5. So just pause it. I'm going to carry right on to the next example to finish it off. There's one more example on here for you to do before actually finishing off your assignment. So make sure you're comfortable with this, and then you can continue on the video. So the last example is, at what distance from the moon's surface is the gravitational field strength equal to 1.32 Newton kilograms? Okay, so we have, I'm just going to grab a lot of this. Okay. We want to know what distance from the moon's surface. So at what distance from the moon's surface? This is altitude, which is the same thing. We go back here. This in here is altitude. It's the distance above the surface of the planet. So we want to find altitude. We want gravitational field strength equal to 1.32 Newton kilograms. So we need the mass of the moon from our sheet, and we need the radius of the moon from our sheet. So the moon information is on the second side of the sheet. Go to Earth, and this is the information about moons. So there's 6 planets on there, or 6. Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And then it's the most common moons, and then information about them. So the mass of the moon is 7.35 times 10 to the 22 kilograms. And the radius of the moon, equatorial radius is 1.737 times 10 to the 6 meters. So just to reiterate what we're trying to find here, we have the moon, and the moon has its radius, as I've labeled over there. And so we have some spot out here where G is equal to 1.32 Newton kilograms, and we want to know how far away that is. So we want this distance here. So what we're going to do is solve for R in the equation, then we have to subtract off the radius of the moon. So if we start with G equals big G m over R squared, and we rearrange this to solve for R, R is going to be equal to the square root of G m over G. So the square root of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of the moon, which was 7.35 times 10 to the 22 kilograms, divided by with 1.32 Newton kilograms. So that gives us 1,927,168 meters. So what that distance is this whole distance here, the whole thing. Okay, that's 192,716.8 meters. So in order to find the altitude, so altitude is going to be equal to R minus R of the moon. So 1,927,168 meters minus 1.737 times 10 to the 6 meters, which will give you 1.90 times 10 to the 5 meters. Great. And you can finish off the practice questions there. Now you have all the information to finish it all off. So the 1 to 5, any of that you didn't finish in the previous stop of the video, and then 6 to 12, you can spend the rest of the class working on that. Thanks, guys. Hope you have a really good 5-day break, and I'll see you on Wednesday.